Alright, we are in the home stretch here. We are, in this last problem, we are looking at a graph and we are trying to determine what the average rate of change is for the graph. So it looks like our scenario here is a little snail who's moving along from his home. Who knew snails had homes? I thought they just... never mind, who knows what I thought. I don't know anything about snails. Anyway, this chart represents the distance that this little snail is moving away from his home. So, did I say rate? It represents the distance he is from his home. The rate is actually represented if we measure the change in y, the rise, and divide it by the change in x, the run. And so, let's take a look at a few things that this chart tells us before we start number crunching here. Our x-axis tells us distance. So therefore, any change in x will really be our change in what? Millimeters. So it'll be change in millimeters. Oh, I'm so sorry. That's not the x-axis. That's the y-axis. Any change in y will be any change in our millimeters, and any change in x will be our change in seconds. So therefore our rate, if we divide the change in y by the change in x, the rate will be millimeters per second. Do you see how that fraction, this fraction here, tells us that it's millimeters per second. So that's how our rate is going to be expressed. We looked at the units that each of these axes are measured in, and it's the rise divided by the run, which tells us what the unit is. So let's go ahead and for each one of these see what the rise over the run is. So between 0 and 4 seconds, our 0, here's our 0 and here's our 4. So our rise was 5. 10, where should I write that? We'll go 10 millimeters divided by our run. This was 10, and our run was 1, 2, 3, 4 seconds. Our rise right here is 5, 10 again, and our run was 2, and so in this instance our rise over our run will be 10 over 10 millimeters over 2 seconds, which equals 5 millimeters per second. So I'll go ahead and write 5 millimeters per second. And let's see here, this one was 10 millimeters per every 4 seconds, and I'm just too lazy to divide that out to get the unit rate. Number 24, between 6 and 7 seconds, it looks like our rise is 10 units divided by 1 unit. So remember, our units on our rise is our millimeters, so that's 10 millimeters over 1 second, so 10 millimeters per second. Between 7 and 10 seconds, it was just flat, so what was the rise? Rise over run. Our rise, there was no rise. Our rise was 0. So our snail went 0 millimeters, and how long? For over how long? 1 second, 2 second, 3 second. Per 3 seconds. So our snail stood still for 3 seconds. So his rate here was 0 millimeters per second. And let's look at this one here. 5, 10, 15 was the rise, and the run was 1, 2. And remember, don't forget our units. This was 15 millimeters and our run was 2 seconds. So our snail, between 10 and 12 seconds, traveled a distance of 15 millimeters per 2 seconds, which equals 7.5 millimeters per second. And lastly, look. It looks like our snail went back towards his house because this is a negative rate. And we'll see that because we rise a negative distance. We go down. Our rise is -5. And our run was 1, 2, 3 seconds. Was 3 seconds. So our rise over our run is -5 millimeters for every 3 seconds. So the big idea to keep in mind when looking at a graph and determining rate of change is, don't forget that rate of change is rise over our run, and that units are incredibly important because that's what conveys what the rate means. So we look at our rise, we measure our rise, and then we measure our run. And we put our rise, and we then divide it by our run, and that is what our rate is. That is the review for test number 4. Come and see me with questions, and study hard. So long.